Relation between Maxwell-Boltzmann, Bose-Einstein and Fermi-Dirac statistics. Statistical mechanics can be divided into two, that is classical statistics and quantum statistics. Maxwell-Boltzmann distribution law can be included in classical statistics, but quantum statistics can be divided into two, that is Fermi-Dirac statistics and Bose-Einstein statistics. Next is the comparison between Maxwell-Boltzmann statistics, Bose-Einstein statistics and Fermi-Dirac statistics. Maxwell-Boltzmann statistics is originated before quantum statistics. In the case of Maxwell-Boltzmann, spin can have any value. But in the case of Bose-Einstein, only integral spins are possible. That is 0, 1, 2, 3, etc. But in the case of Fermi-Dirac, half integral spins are possible. That is half, 3 by 2, 5 by 2, etc. Maxwell-Boltzmann particles are identical and distinguishable. But Bose-Einstein as well as Fermi-Dirac particles are identical as well as indistinguishable. In the case of Maxwell-Boltzmann, no restriction is imposed. Consider the case of two particles A and B. We take A and B because in this case the particles are distinguishable. These two particles can be arranged like this, that is, can be arranged in four ways. In Bose-Einstein statistics also, no restriction is imposed. But we are considering two particles. In this case, we are considering two particles A and A. We take A and A because these are indistinguishable. These two particles can be arranged in three ways. That is, this A and A can be arranged in three ways. But Fermi-Dirac statistics follow Pauli's exclusion principle. Consider the case of two particles A and A. Since they follow Pauli's exclusion principle, these two particles can be arranged like this. In the case of Maxwell-Boltzmann, new microset is obtained when we interchange the particles. But in the case of Bose-Einstein as well as Fermi-Dirac statistics, the particles are identical and indistinguishable. Therefore, no new microset is obtained. In the case of Maxwell-Boltzmann statistics, size of the cell in phase space is arbitrary. But in Bose-Einstein and Fermi-Dirac statistics, size of each cell is fixed and definite. And the number of phase cells in a given volume is also fixed. The thermodynamic probability in the case of Maxwell-Boltzmann statistics is n factorial into product of I a raised to ni divided by ni factorial. In the case of Bose-Einstein statistics, the thermodynamic probability is ni plus j minus 1 factorial divided by ni factorial into j minus 1 factorial. But in the case of Fermi-Dirac statistics, the thermodynamic probability is j factorial divided by ni factorial into j minus ni factorial. The number of particles in the ith stage in Maxwell-Boltzmann statistics is ni is equal to gi by e raised to alpha plus beta ea. In the case of Bose-Einstein statistics, the number of particles in ith stage, that is ni is equal to gi by e raised to alpha plus beta ea minus 1. But in the case of Fermi-Dirac statistics, ni equal to gi by e raised to alpha plus beta ea plus 1. Although the distribution laws are different, there will be a certain condition under which all the three distribution laws will yield virtually identical results. This will occur if Gi by Ni is large in comparison to unity. So that Gi by Ni plus 1 approximately equal to Gi by Ni, that is also approximately equal to Gi by Ni minus 1. Under these circumstances, all the three equations for the different distributions will become equivalent to Boltzmann distribution law. In general, it can be stated that provided the temperature is not too low or the pressure too high, the number of quantum states, that is Gi, is large in comparison with the number of particles, that is Na. That is, in this case, Gi by Ni is much greater than unity. Therefore, for almost all conditions under which normal gases exist, the classical Boltzmann distribution law should be adequate to describe their actual behavior within the possible limits of experimental observations. There are, however, a few cases in which the Boltzmann distribution law is not applicable. That is, radiation, liquid helium, electron gas in metals, etc. Boltzmann distribution law is applicable to any ordinary gas at low temperature except the cases of hydrogen, helium and neon, and apply even to these gases at relatively higher temperature. It fails in the situation when density is very large. It also fails in the case of electron gas in metals. It can be applied to metals only at temperatures far above the melting point of metals. In cases where Boltzmann distribution law fails, FD or BE distribution law can be applied depending upon whether the system is composed of bosons or fermions.